Hi everyone, my name is Kirsty and I will be talking about my research. I'll walk you through my research and we'll start with the introduction to the Eastern Massasauga. The Eastern Massasauga rattlesnake is one of two rattlesnakes native to the Great Lakes. Our study area is Carlisle Lake in Clinton County, Illinois. It is where one of three extant EMR populations currently lives. It's about 50 miles east of St. Louis, and it's actually Illinois' largest man-made lake. It was originally created as a reservoir by the Army Corps for maintaining navigational levels on the Mississippi River via the Kaskaskia River. The surface area of the lake itself is about 150 square kilometers, and the surface area of the entire study area is about 650 square kilometers.
So Carlisle Lake is located in a moderately susceptible area to winter droughts and summer flooding, and that's largely driven by climate change and then human alterations to the landscape. So we need to understand how these droughts are going to affect the habitats that the Massasauga uses and what land cover types are most vulnerable to changes over time. So the study will model 5 important land cover types under 3 drought scenarios, and this is going to be your baseline, moderate, and heavy drought scenarios. So we're going to model suitable land cover types, so this is going to be bare ground, emergent wetlands, and then scrub shrubland. We're also going to model the somewhat suitable land cover types, which is the upland hardwood, and then a non-suitable land cover type, which is going to be developed. So our hypothesis is that suitable habitat will decline as drought intensity increases.
So land cover data was first downloaded from the NLCD database for the latest years, which was 2011, 2013, and 2016 in a raster format. Each year's dataset was then added to a map in ArcGIS Pro and reclassified into 8 classes, which were unclassified, water, developed, bare ground, upland hardwood, lowland hardwood, shrub, scrub, and emergent wetland. So this is basically all of the suitable habitat, but then also unclassified and water, which we later took out. To determine the probability of each land cover type transitioning to the next, I used the Tabulate Area tool in the Spatial Analyst toolbox in ArcGIS Pro to generate an output table that has the land cover categories in rows and columns between 2011 and 2013, as well as between 2013 and 2016. So 2013 and 2016 was chosen as our baseline model, as that was more indicative of the new normal state that we're living in. The 2011 and 2013 pair was chosen to represent the moderate drought scenario, as the state of Illinois endured a moderate to severe drought for much of 2012 and part of 2013. So while the time difference between the two models is different, we can use this as a good generalization. The output of the tabulated area was then exported to Excel for additional analysis. And to represent a heavy drought scenario, we used a few assumptions here in creating this third P matrix. And that was really created based off the difference between the baseline and the moderate drought, with a 1% wetland loss and a 1% bare ground gain. And that's also incurring no shrub or scrub conversion. So this is essentially a worst case scenario. Prior to calculating these transition probabilities, the unclassified and water classes were removed in addition to the lowland hardwood land cover, as that study area didn't contain any lowland hardwood land cover. The Markov model was then run through each matrix with a time step of 3 years, and that's based on the 2013-2016 baseline. The results were then analyzed and visualized in R using FSA and ggplot packages. So Markov models are stochastic models, and they're used to model pseudo-randomly changing systems with finite states that are not dependent on their previous states. They've been widely used in the field of landscape ecology as simple, non-spatial models. For this experiment, we can model the probability of future states based on our 3 scenarios, and that's going to be our baseline, a moderate drought scenario, and then also a heavy drought scenario. So on the left, you'll see the state transitions that follow ecological succession. So bare ground goes to emergent wetland and so forth. And then at any point, any of these states could essentially become developed, whether that's for agriculture or for building homes or whatnot. And on the right, you'll see the transition probabilities for each state in the scenario. I won't delve into this too much, but this slide just shows the methodology that I use for the statistical analysis. And then these tables show the results from the statistical analysis. So we can see that the means between each population, so each state variable, were significantly different from one another. And then also those states within each scenario, those pairs were also all significantly different from one another. So this basically tells us that every single possible combination was significantly different from one another.
Each model yielded a very different prediction for the future. Please note that bare ground and shrub scrub are plotted on the y-axis on the right since they're over an order of magnitude different than our other land cover types. So for the baseline scenario, we essentially lose all of our bare ground by 2655. You can see this severe drop over the next few hundred years. We also see about a 9% gain in developed land, and we don't see a change in the emergent wetlands. We also see a slight 4% decrease in upland hardwood habitat and about a loss of 32% of shrub scrubland habitat by 2655. For the moderate drought scenario that was derived from transitions from the 2011 NLCD data and the 2013 NLCD data, we see some different trends than we did from the baseline, the 2013 to the 2016 model. So developed land, upland hardwood, and emergent wetland do not change in this scenario, whereas we lose about 40% of our bare ground and about 92% of our shrub scrubland. So it looks like most of the area that the Massasauga would occupy in the summer is going to be lost under this moderate drought intensity. As one can assume, we see the most dramatic changes in our heavy drought scenario. This is also one where we went with a few assumptions when creating this transition probability. We see developed land increase by about 21%, and then here upland hardwood doesn't change, similarly to the moderate drought scenario as well. But bare ground increases threefold. Now remember that we did have a 0.1% increase in bare ground, but it's amazing to see how it increases. It kind of peaks around 2,300 and then kind of steadies out more towards the end nearing 2,600. We also see that emergent wetlands decline by about 19%, and that's incurring a 1% loss every 3 years. And we also lose nearly all of our shrublands. So again, that habitat that the Massasauga is going to occupy during the summer.
By looking at these box plots for each state variable, we can compare the range and distribution of the mean between each scenario to visualize just how different these results are from one another. We can also see the variation that happens within each scenario as well. For example, emergent wetland land cover, we see hardly any variation at all in the baseline and moderate drought scenarios, whereas we see a lot of variation and an overall lower mean in the heavy drought scenario. We can also see these differences too for these additional state variables. So for scrubland cover, we see that there's very little variation within each scenario, but between the scenarios there is. The means are pretty different. Same goes for the bare ground land cover, where we see a little bit of variation within each scenario, but overall each mean is very different, which this could also be an indication that we should try a different statistical test, or we should try fine-tuning our model a little bit more in our validation step. All models yielded significantly different results, which indicates that small changes in land cover can have large changes over time. So in all three scenarios, we see that our hypothesis is correct and that there is significant loss of suitable habitat as drought intensity increases. We see this as the shrubland decreases in both the baseline and the moderate drought scenario, as well as the heavy drought scenario as well. We also see a significant loss in bare ground in the baseline and the moderate drought scenario. It's not until we start adding bare ground as we're losing emergent wetland in the heavy drought scenario that we actually see an increase there. Interestingly enough, we see that in the baseline and the moderate scenario, wetlands do not change. It's not until we start seeing a loss due to heavy drought that causes a change there, which this can be good. Illinois has a no net loss wetland approach, which is great, but they've also lost about 90% of their wetlands since the 1900s. So there is definitely room for Illinois to practice restoration to increase the wetlands as well. Because they're losing so much shrubland and then also bare ground, this could really pose a risk for Massasaugas in the summertime, when that's where they're really using that space to regulate their body temperatures as well. We also see that we're just losing a lot of land, and we don't really know where that's going. It's most likely going to agricultural conversion, but again, this is a simple model, so we don't necessarily know how that land is being shifted. This is also yearly data too, and we don't necessarily know how the land is changing interseasonally, and we really need to understand that to understand where the Massasaugas are going to be and when too. So there's definitely more room to move towards a spatiotemporal model that can also include those sorts of variables. Given that the eastern Massasauga is a federally endangered species, we definitely need more research to understand the distribution of this rattlesnake. With climate change becoming more and more perilous, we need to understand how it's moving through the landscape and where it's going to be in order to have more timely and accurate habitat management. Given how droughts are becoming more and more common, this might also involve working with local agricultural managers and farmers to lessen the impact of drought and hydrologic changes as well. We also need to increase our education too, so people can become protectors of the eastern Massasauga rather than predators. Thank you so much for your time today.